20 minutes to no laser cutting machine bed production process. For the complete laser cutting machine, we can all picture their fast-moving laser heads, spectacular sparking cuts, micron-level precision, and 24-hour non-stop operation. These achievements of modern industry embody the crystallization of human wisdom. In the field of CNC machining, what are the unique characteristics of the laser cutting machine bed compared with other conventional machine tools? First of all, the movement speed and acceleration are not on the same order of magnitude at all. Laser cutting machine speed 601 to 0 min, acceleration 0.3-1 g. The gantry frequently starts and stops abruptly during back and forth movement. Conventional lathes milling machines machining centers speed 10-30 min, low acceleration and smooth movement. Second, the force application mode is different. Laser cutting machine, the beam is suspended and the cutting head moves at high speed in midair, resulting in significant overturning moment and torsional deformation. Conventional machine tools, the cutting tool or workpiece is close to the bed with concentrated and stable force. The thermal influence is completely different. Laser cutting machines have two major heat sources: heat generated by the laser, high-temperature radiation from molten metal slag during cutting. Guide rails and racks are exposed to heat for a long time. Once the bed heats up, it deforms and precision is directly lost. Conventional machine tools generate little heat during cutting and have stable heat dissipation. The differences between the two are further reflected in different precision requirements. Laser cutting machine, positioning accuracy 002 m, repeat positioning accuracy 001 mm. Conventional machine tools, a precision level of 0.1 mm is sufficient for most applications. Different structural forms. Laser cutting machine, gantry structure dual drive. Conventional machine tools, slant bed, flat bed, fixed column, C-frame. Different requirements for long-term continuous operation. Laser cutting machine, 24-hour non-stop operation, high-speed reciprocating movement and continuous vibration. Conventional machine tools are mostly used for intermittent processing. Thus, this machine tool is far more than just a frame assembled from steel. It is a solid guarantee of precision, efficiency, and stability. What technical measures have engineers adopted to achieve such precise control? Next, let us step into the production process to find out. The entire bed production process covers 10 core steps. Process 1, raw material selection and technical planning. Process 2, material cutting and rough machining. Process 3, bed assembly and welding. Process 4, stress relief treatment. Process 5, surface treatment. Process 6, precision machining. Process 7, assembly. Process 8, finished product inspection. Process 9, aging testing. Process 10, packaging. Each step strictly complies with international standards and professional industry specifications. Preparation stage, raw material selection, and technical planning. In the raw material selection stage, high-quality, low-carbon alloy structural steel is mainly adopted for laser cutting machine beds. Priority is given to Q355B low-alloy high-strength steel and Q235B ordinary carbon structural steel. For high-end models, 45 steel or alloy cast steel can be used to meet higher performance requirements. The core basis for material selection is the equipment tonnage, cutting power, and actual application scenarios. To strictly ensure the rigidity and deformation resistance of the machine tool, what key requirements must be met starting from the source materials? Material requirements. Carbon content controlled at 012-020, sulfur and phosphorus impurity content 0.045% to avoid welding cracking and insufficient toughness caused by excessive impurities. Tensile strength 345 megapascals, yield strength 235 megapascals to ensure the load-bearing capacity of the machine bed. Steel specifications. According to the bed dimensions, thick steel plates with a thickness of 8 mm to 30 mm are selected. For large machine tool beds, spliced steel plates can be used. Quality inspection. After the raw materials are received on site, ultrasonic flow detection must be carried out to inspect internal defects such as air pores, cracks, and laminations in the steel. The key to technical planning lies in completing the scientific and rigorous bed structure design and detailed drawing decomposition based on different models of fiber laser cutting machines, combined with their cutting range and motion speed. With all preparations completed, let's begin the first process. Process 1, material cutting and rough cutting. Material cutting is the first processing procedure in bed production. Its core purpose is to cut thick steel plates into blanks that meet the drawing requirements, with emphasis on controlling dimensional accuracy and cut quality, so as to avoid excessive dimensional deviation of blanks and increase the difficulty of subsequent processing. Selection of cutting equipment and parameter setting. According to the thickness and size of the steel, select the corresponding cutting equipment. The mainstream equipment includes CNC flame cutting machines and CNC plasma cutting machines. For high-end models, high-precision fiber laser cutting machines can be used. Material cutting, practical operation, and quality control. During the cutting process, observe the cut condition in real time and adjust the cutting speed and gas pressure promptly to avoid defects such as cut deflection, dross adhesion, and cracks. For spliced bed frames, cutting of the splicing grooves is required. After cutting, measure the length, width, thickness, and diagonal dimensions of the blank using a tape measure, caliper, and level gauge. The dimensional tolerance shall be controlled within 0 to m. Check the perpendicularity and roughness of the cut surface. Unqualified blanks shall be subjected to secondary cutting or grinding correction. Finally, use an angle grinder and bench grinder to remove burrs and dross from the cut surface to ensure a smooth cut, preventing burrs from affecting subsequent welding and precision machining. Process 2. Bed frame splicing and welding. Welding is the core process for forming the bed frame. Its purpose is to splice the cut blanks and stiffeners into a complete bed frame structure. The key requirements are high welding strength, good weld quality, no welding defects, and minimal welding distortion. Welding preparation. Workpiece pre-treatment. Clean the welding surfaces of the spliced blanks and stiffeners with sandpaper and a wire brush to remove rust, oil, and oxide scale on the surfaces, ensuring the welding surfaces are clean. Welding material selection. Select electrodes or welding wires matching the material of the bed frame. Electrodes must be kept dry and should be pre-baked to remove moisture as much as possible to avoid porosity during welding. Fixture and tooling fixing. Assemble the blanks and stiffeners in accordance with the drawing requirements, and clamp and fix them firmly with tooling fixtures to ensure assembly accuracy. For large bed frames, adopt sectional assembly and sectional welding to prevent assembly deviation. Welding procedure. Welding of the laser cutting machine bed adopts a combined method of submerged arc welding and gas-shielded welding as a priority. Submerged arc welding is used for bed body splicing and long welds high efficiency, stable weld quality. Gas-shielded welding is used for stiffener welding, corner areas, and weld repair strong flexibility. Welding sequence. Follow the principles of inner first, outer later, lower first, upper later, short first, long later. Weld the internal stiffeners of the bed frame first, then the external splicing welds. Weld the bottom welds first, then the side and top welds. Weld the short welds first, then the long welds, so as to avoid deformation of the bed frame caused by concentrated welding stress. Weld quality control and inspection. For weld inspection, visually inspect the weld surface with naked eyes or a magnifying glass. The weld surface shall be smooth and continuous without defects such as cracks, porosity, slag inclusion, incomplete penetration, and undercuts. Ultrasonic testing shall also be performed on the bed body splicing welds and main stressed welds. Unqualified welds found during inspection shall be repaired. Before repair, the defective areas shall be removed completely, and the number of repairs shall not exceed 2 times. Process 3. Stress relief treatment. During the welding process, a large amount of welding stress is generated inside the bed. If stress relief treatment is not carried out, the bed may deform, crack, and suffer other defects during subsequent precision machining and operation, which will directly affect the accuracy and service life of the laser cutting machine. Vibration stress relief treatment. Vibration stress relief treatment applies periodic vibrations to the welded bed frame through vibration equipment, so that the internal welding stress in the bed frame is gradually released and evenly distributed, thereby achieving the purpose of stress relief and dimensional stability. Compared with stress relief annealing, the intelligent vibration stress relief instrument features high processing efficiency 30-60 minutes per piece, low energy consumption, and no environmental pollution. In addition, it does not alter the mechanical properties of the bed material, making it suitable for mass production. Stress relief annealing. Stress relief annealing involves placing the welded machine bed into an annealing furnace. Through gradual heating, heat preservation, and slow cooling, the internal welding stress of the bed is fully released to achieve dimensional stability. Equipment selection. Trolley-type annealing furnaces are adopted. The furnace chamber size is customized according to the bed dimensions, with a temperature control accuracy of 5, enabling automatic heating, heat preservation, and cooling. After stress relief annealing is completed, the internal stress of the machine bed is inspected. A stress relief rate of 90 is considered qualified. Compared with vibration stress relief treatment, annealing achieves more thorough stress elimination, which can effectively prevent deformation of the machine bed during long-term use. It is suitable for large-scale, high-precision laser cutting machine beds. The disadvantages are high energy consumption, long processing cycle 4-8 hours per piece, and relatively high cost. Process 4. Surface treatment. The core purpose is to provide effective corrosion and rust protection for the machine bed while enhancing the cleanliness and texture of the overall equipment appearance. This effectively extends the service life of the bed, enabling the equipment to easily adapt to various complex working conditions such as humid workshops and temporary outdoor operations, ensuring stable and reliable performance at all times. Next, we carry out surface pretreatment to thoroughly remove impurities and greatly improve coating adhesion. We adopt the mainstream sandblasting derusting process in the industry, using quartz sand or emery abrasive. Through high-pressure spraying, we completely remove rust, scale, and welding spatter from the surface of the machine bed. Mainstream surface treatment processes. At present, there are two mainstream surface treatment processes for machine beds. The first is electrostatic powder coating. Powder coating is evenly adsorbed onto the bed surface using the principle of electrostatic attraction, then sent to a curing oven for high-temperature baking to fully melt, level, and cure the coating. After cooling, the coating appearance, thickness, and adhesion are inspected item by item, finally completing surface protection and exterior finishing. The second is paint spraying. A matching polyurethane topcoat system is adopted. Primer is applied first, and topcoat is sprayed after full drying. The strict matching use of primer and topcoat effectively improves coating adhesion and anti-corrosion performance, ensuring resistance to peeling and rust during long-term service. Process 5. Precision machining. Following the completion of preliminary pretreatment, precision machining becomes the critical process that determines the accuracy of the machine bed. It directly affects the operational precision and stability of the laser cutting machine and must be performed in strict accordance with standard specifications. Its core task is to conduct precision machining on key surfaces such as the bed guide rail mounting surfaces and gear rack mounting surfaces. Using professional equipment, strict control is maintained over dimensions, flatness, and surface roughness to eliminate deviations and ensure compliance with requirements. This process serves as important support for ensuring stable operation and accurate positioning of the laser head, as well as achieving high precision, efficient, and stable operation of the entire machine. First, the bed workpiece is hoisted onto the workbench of the gantry milling machine, aligned and leveled with a spirit level and a dial indicator, and then firmly clamped and fixed. Subsequently, following the process sequence of rough milling, semi-finish milling, and finish milling, high-precision milling is performed on key fitting surfaces such as the guide rail mounting surfaces, rack mounting surfaces, and motor base surfaces. Surface coatings are removed, and dimensions as well as geometric tolerances are machined to meet design requirements. After machining is completed, special inspection tools are used to inspect flatness, parallelism, straightness, and surface roughness item by item. Once all indicators are qualified, the workpiece is cleaned and transferred to the next assembly process. Process 6. Assembly. Assembly is the process of assembling the precision machine bed with related components, guide rails, gear racks, bearings, protective covers, etc., into a complete bed assembly. Pre-assembly preparation is an important prerequisite for ensuring the accuracy of the complete machine. First, all parts are fully inspected, with their models, dimensions, and precision indicators verified to ensure full compatibility with the machine bed. Meanwhile, various special assembly tools are prepared to guarantee a standardized and efficient assembly process. Bed cleaning is also critical, and hydrous ethanol is used to carefully wipe key mating surfaces such as guide rail mounting surfaces and gear rack mounting surfaces, thoroughly removing dust, oil, and impurities to keep the assembly surfaces highly clean, laying a reliable foundation for subsequent high-precision assembly. Machine tool assembly is carried out in strict accordance with the principles of inner first, outer later, lower first, upper later, core first, auxiliary later. First, core transmission components such as guide rails and gear racks are assembled. When installing the guide rails, a torque wrench is used to evenly tighten them to the specified torque of 40-60 Nm, and a dial indicator is used to calibrate the straightness and parallelism of the guide rails, ensuring the total length deviation is no more than 0.005 mm per meter. During gear and rack assembly, the meshing clearance is finely adjusted to 0.1-0.2 mm to ensure smooth meshing, stable transmission, and no jamming. After the core components are assembled, auxiliary parts such as bearings and sealing rings are installed in sequence. Lithium-based grease meeting machine tool lubrication standards is evenly applied to moving pairs including guide rails and bearings. Seals are installed on joint surfaces and moving parts to provide reliable dust and dirt protection, keeping the internal structure clean and stable. Finally, appearance and protective components such as protective covers, cable ducts, and junction boxes are assembled, completing the overall machine tool assembly. Process 7. Finished product inspection. Finished product inspection is the final acceptance process in bed production. Its core purpose is to comprehensively inspect the dimensional accuracy, mechanical properties, operational stability, and other indicators of the machine bed, ensuring that every product meets design requirements, international standards, and customer needs. After a series of precision machining and assembly, we arrive at the final acceptance checkpoint in bed production: finished product inspection. This serves as the last line of defense for product quality, allowing no room for carelessness. The first category is dimensional accuracy inspection, which focuses on verifying dimensional parameters and geometric tolerances of key bed areas to ensure full compliance with design standards, providing precise assurance for complete machine assembly. The second category is operational stability inspection, which simulates actual working conditions to verify smoothness and stability after bed assembly, eliminating problems such as jamming and deviation. The third category is surface quality inspection, which carefully examines the bed's surface coating and flatness to confirm no rust, defects, or scratches, balancing protective performance and aesthetic appearance. A special note is made here regarding the disposal procedures for non-conforming products. If any single indicator fails to meet the required standards during inspection, the product shall be classified as non-conforming. We will immediately analyze the causes of non-conformity, such as insufficient precision, peeling surface coating, etc., and carry out targeted rework. Upon completion of rework, the product must undergo a full re-inspection until all indicators are qualified before proceeding to the next process. Process 8. Aging Test. Following strict finished product inspection and non-conforming product handling, we proceed to the 8th process: aging test. This is the ultimate test for the machine bed before delivery, designed to build the last line of defense for the long-term stable operation of the equipment. The core of the aging test is to simulate the actual working state of the machine bed under real operating conditions. Through long-term continuous operation, it comprehensively verifies the stability, durability, and reliability of the bed, identifies various potential failures in advance, and fundamentally eliminates problems such as deformation, abnormal noise, and accuracy degradation during long-term service. This ensures that every piece of equipment delivered to customers is stable and durable. We use a professional aging test bench, which can not only accurately simulate the actual working load of the bed, but also is equipped with a complete temperature and humidity control system. It can flexibly simulate different application environments such as humid workshops and outdoor sites, making the test scenarios more consistent with actual usage requirements. The test procedure is also strict and standardized. First, the qualified bed assembly is accurately installed on the aging test bench and connected to the control system. Exclusive test parameters are set according to actual working conditions to restore the daily working environment. Then the test equipment is started for uninterrupted aging testing. Small beds are tested for no less than 24 hours, while large beds are extended to more than 48 hours. During the test, the bed's temperature variation, vibration amplitude, and accuracy fluctuation are monitored in real time throughout the process, ensuring that every piece of data is traceable and every bed can pass the stringent test. Process 9. Packaging. After passing the stringent aging test, we enter the final step of production packaging. This serves as a safety escort for the machine bed on its journey from the factory to the customer, and every detail directly affects the integrity of product delivery. The core purpose of packaging is clear: to provide all-round protection for the machine bed, effectively preventing damage such as collision, scratching, and rust during long-distance transportation and storage. This ensures that each machine bed reaches the customer in perfect condition, without affecting subsequent assembly and operation. Finale. This completes our overview of the production process for laser cutting machine tools, from initial groove machining and leveling to precision welding and surface treatment, followed by finish machining, assembly practice, finished product inspection, and finally aging testing and packaging. The 9 processes are closely linked and tightly controlled at every stage. Alright, YouTube family, that wraps up this video. We're just getting started, and we welcome insights from all fellow industry experts. Stay tuned for upcoming videos covering laser source principles, the future of robotic welding vs. manual welding, and more industrial tech content. Don't forget to subscribe for updates.